Okay. Welcome to the monthly meeting of the Howard Astronomical League for February. This is Victor Sanchez. I am the new incoming president, and I'm thrilled to be the president and part of HAL. So let me see if I can share my screen and we can kick off the meeting. How do I do that? Share screen. That's not right.
And we'll get to see which screen you're sharing.
Okay. Does that look right?
Right one.
Right one, yeah. All right. So yes, welcome everybody. We have a really interesting speaker. It's right out of the movies, science fiction. And I think we have a new agenda that we're going to give a try. And I'm super excited to be the club president. At some point, I'll feel comfortable and I'll start asking for more, inputs from everybody in terms of what to do with the club and if any changes. But for the most part, I think Phil did such a good job that I'm going to just try to stay up to par with what he did and keep the club going like that. So, but I'm really open to, any changes or thoughts. So if you ever have any ideas on what you'd like to see or new things in the club, please reach out. You can send it to my VCS email account, my Yahoo account, or to president@howardastro.org. Anyways, El Presidente. Okay, so let's get on with the meeting. Here's our agenda for tonight. I guess I'd like to do some introductions. If anybody's new, then please speak up and say hi and introduce yourself if you like. If you're shy, you don't have to. Any new members? Any guests? Okay. Well,
somebody, I think Al was raising his hand, Victor. So
okay.
you just have to unmute and say hello.
Oh, okay. Now I'm getting it.
Am I on mute? Can you hear me?
Yes, we can.
Okay, great. Hi. First of all, Victor, congratulations.
Thanks.
So I was here last month's meeting, but I got distracted during the introductions of new members. But anyway, what can I tell you? I'm a transplant from Pennsylvania, and I've been out of the hobby for about 10 years, and found your club online, and I'm just excited to be part of it, and I want to try to get more involved in it again. So hi everybody.
So did you send me it's Al Francis, you sent me the solar picture?
Yes.
I'm very excited to show that. That is one of the most amazing astro photos of the sun I've ever seen. So
Well, thank you. No, I'm new to solar imaging too. So I mean, I think throughout the hobby, I've pretty much, I won't say I've done it all, but I've started off visual back in the 80s, did the piggyback with film photography, did the ATM where you grind optics and all that stuff. And then even the business part of the hobby, got into that with and then the observatory, the deep sky imaging. I've done it. I mean, I can't say I've done it all, but I've tried it all.
well, that's terrific. And I'm looking forward to interacting more with you and maybe learning some from all of your experiences. So welcome to the club.
Well, thank you very much, and congratulations to you, sir.
Yeah, thanks. Trevor, you want to say hello?
Yep. Hi, I'm Trevor. I joined on Saturday after picking up a card at the Company 7 Astro Optics, where I was looking for eyepieces to try to give myself a better chance of spotting that darn green comet in my 114 millimeter Newtonian. Didn't work out, but they helped me collimate the thing, which greatly improved my views of the planets. So it was a worthwhile trip, and only ever done visual astronomy. Interested in learning more about taking pictures, and yeah, excited to meet a new group of people.
Great, terrific. This club does a lot of astrophotography, and but there's a few diehard eyepiece people who love to stay at the eyepiece, and you'll see as we move along, or as you get involved in the club, we have star parties where we share views with people, and there's all sorts of eyepiece viewers, and Newtonians are great for that, so welcome. Okay, so the rest of the meeting, what am I sharing? Am I still sharing my screen? Yeah. Okay, so the rest of the meeting will.
You're not in presentation mode though.
Right. So I was trying to
There you go.
Now we're seeing, yeah, your presenter mode. There you go.
Yeah, I was trying to figure out where the all the Zoom people had gone behind the background. So anyways, we have a few announcements to make, and then we're going to talk about what's out in the sky, and then we're going to turn it over to our featured speaker, Dr. Angela Stickle, and then we'll go over some pictures and then wrap up. Hopefully we'll have time that we can all sort of chat for a while before our 9 o'clock deadline. So announcements, star parties. This is the schedule of our HAL star parties for this year. We start in March. For those of you who are new, generally have one members and one public star party a month. The members are generally for people to just kind of go set up their own equipment, have access to the park, which has pretty good horizon views and relatively dark skies for around here. And maybe just sort of do some visual, check out new gear, talk to people, pick up tips. And then the public star parties, these photos are from a public star party where you might have multiple scopes set up outside, and then people coming inside to look through the at the display from the big telescope. So anyways, yeah, these are the dates, and stay tuned. It's gonna get warm soon, and we can get started. And then
just a quick note, Victor, if anyone has just received the Howard County Activity Guide from Recreation and Parks, we and they are aware that there are some misprints, but this is the correct schedule, and is on our website is the correct schedule.
Right, thanks. And are they correcting the actual hard copy prints, or they're just going to update their website?
No, I believe that's already out, but the website will be updated. We got confirmation on that today.
Okay. And then I just put up, I think that there have been a few emails on the email distribution list, but I'm just putting up some regional star party dates too, in case anybody's interested. And and just as a heads up, Phil and I went out to a relatively dark site, and we haven't figured out how to do it, but I'm going to try to have our own like dark sky star party. I'll look for announcements on that. We're still working out how to do that. Anyways.
Yeah, and I also want to remind people, if you don't mind, that for members of HAL, we also have impromptu star parties that can be called pretty much, early in the day that they are going to be held depending on the weather. So if you're interested in observing, please make sure you're signed up. If you're a HAL member, sign up for the impromptu list.
And you do that via the website. Okay, so now let's a couple other announcements. Phil is going to be starting up Astro School again. You want to speak to this?
Right. So a number of years ago, we were discussing this here. I think maybe it was Chris Miskowitz who might have started this a long time ago. And then Bob Savoy took it and ran with it. And it's basically session where we have a topic and we have a subject matter expert to lead that topic. And it used to take place an hour before this meeting started when we were holding the meetings in the Robinson Nature Center. And Victor's working on getting us back in there and some kind of schedule. But it was kind of rushed because we couldn't get in before the allotted time. And then we had to get ready for this meeting. So what I'm going to do now is going to have a separate day for Astro School, and it won't be a regular schedule. But what we are going to do when we do have them at the Robinson Nature Center, it'll be the second Thursday of the month, starting at 6:30 p.m. And this is unless we do the Astro School at the observatory when there's nice weather. So at HAL, so in Marriott's Ridge at Alpha Ridge Park. So these topics, what we're going to focus on, they're really what you want. So when we have some time after the end of this meeting today, if you want to hang on for a little while and talk about the topics that you'd be most interested in, then we're going to pick that topic for the next meeting and go from there. So it's really what you want. The last thing I want to say on this is that Bob Savoy and I met with the Robinson Nature People Center at the Robinson Nature Center this week to do a HAL members only planetarium night with a planetarium show that our own Bob Savoy will be hosting. And you have to state the first one is going to be April 13th. There will be more information, and it's going to be first come, first serve. There'll be an $8 charge, and the Robinson Nature Center will have a flyer on how to do that, but it's going to be just for members only for HAL. So when it sells out, and then we'll do another one because there's only 50 seats in there. So that's what's going on with Astro School. So you're going to watch a lot more information coming on this, and we're very excited, and I'm very excited to have Bob Savoy working with me on this. So that's it, Victor. Back to you. You're on mute.
Thanks, Phil.
Yep.
Okay, next announcement.
All right. Hello, everyone. For those of you who don't know me, my name's Crystal. I've taken over the position of librarian. So if you did not know, or if you're new, HAL actually has a collection of books available to members at the location of the observatory at Alpha Ridge Park. So to bring some interest to our collection of books, I believe we have over 400 items available for members to check out. I like to maybe start a series called Book of the Month. So a part of our monthly meetings, I'll do a short little introduction of something that's in our collection that maybe you hadn't heard of, or maybe you're interested in reading. So today I decided to highlight one of my favorite books that will soon be available for checkout, The Glass Universe by Dave Asobo. This book, if you want to say the length, just pure pages that are reading, is about 266, but it actually goes over 300 because this book includes a very large timeline of the Harvard Observatory and the contributions that were made in that time. So one of the things I also feel I will be doing is trying to give you a gauge of what kind of audience this is intended for. For me, I think this is about mid-level, that this is totally, if you're not a super hardcore astronomy person, you could still really enjoy reading this book, but I think you would gain a fantastic appreciation of the historical context if you are familiar with some basic astronomy vocabulary. As far as kind of like a little introduction to the story, if you're not familiar, the subtitle, How the Ladies of the Harvard Observatory Took the Measure of the Stars, refers to the nearly 500,000 glass plates that essentially image the night sky. And this work was largely done by women, which now seems not unusual since astronomy does have a fairly large population of women working in it. At the time, it was revolutionary to have so many women taking on what was primarily a male-dominated field. And so this story goes into talking about starting at the very beginning, when the Harvard Observatory were looking for hiring women to take on the role of what was considered computing, but not your modern computers, but like pen and paper calculations and observations. These roles were given to these women, and progressing through the story, it's an amazing journey and appreciation of the amount of work that these women put into learning about the composition of stars, the classification, creating and developing and elaborating on how we classify stars even in the modern age, and leading us into how photography essentially revolutionized observations. So I really highly recommend this book. It's an amazing read. It's certainly accessible to any level or any background in astronomy, and I think you'll certainly enjoy. And oh yeah, there was a question. This is actually the first book I've ever read by this author. So I know that before the meeting started, some people had mentioned that they have read her other books. So maybe at the discussion part of the meeting, if anyone wants to talk about the comparison, we can open that up. But I highly recommend the book.
Terrific. Thank you. My wife is at her book club meeting right now. I just took a picture of the screen and texted it to her. Maybe they'll adopt it for next month.
Awesome.
Anyways, okay. So next we're gonna try a new thing where we just kind of briefly go over what if the skies ever clear up and we get to go out with our telescopes, maybe you'll get some insight as to what to look for in the next few weeks. So Phil, you're up again.
So I'm going to be brief so we could get on to our guest presenter here. But I'm thrilled to have another solar person in the club with Al. And but what I'm going to do is not about showing my pictures, is talking about what's going on in the sun. And there's an awful lot of solar activity and things in the news. And so I highlighted these 3 items here to talk about. And the first one is, many of you may have seen this story, but it's a big mystery right now where a part of the sun broke off. You can see all kinds of news articles on it from NASA as well as the news bureaus, all the way through to the BBC and everybody. But it turned into this vortex, and you could actually go online and see this vortex spinning. The Solar Dynamics Observatory is what imaged these pictures, and it's quite fascinating. Nobody knows what causes it. Or what has caused it. So this is really fresh news. You can see that this news story was on February 2nd of this year. The second one is that there was a huge solar eruption, and obviously, this particular one is not Earth facing, because you could see it blowing off to the side. If it was Earth facing, it wouldn't look exactly like that, but part of this solar storm at the same time, some was launched towards the Earth, and it knocked out shortwave radio across a good part of the planet. So this happened on February 8th, and this is quite spectacular. And there's some really great pictures taken using different wavelengths that show this eruption. And then finally, this last one, for the first time ever, there were what they're calling sparklers that occurred in the corona of the sun. And when they see these sparklers, and if you look at the left picture on the bottom, in the square, the upper left box there, you can see these sparklers. If you were to look to the right, they're not there. Right, thank you. And then right below that, it's actually showing the solar eruption that took place the day afterwards. The next on the right side there's no sparklers there, and there was no eruption. So they've drawn a correlation. When the sparklers show up, there's an eruption the next day, and once again, they don't understand how that's happening or what it is, because it was witnessed for the first time just recently. So very interesting, and I look forward to bringing you more interesting, timely stories in the months to come. Thank you, Victor.
Thanks, Phil. Bob.
There you go. I'm trying to unmute myself. I'm going to talk about the moon, and I don't know how this is going to work out, but I'm going to start by doing one feature each meeting, one notable feature on the moon that you may not have looked at or may not have thought about looking at. And I started with Petavius crater, which is way over on the right side of the moon. You can only see it one day per month, the third day after new moon. So it sets very quickly after the sun sets. So you don't have a lot of time to look for it. It won't even be a dark sky. It'll still be a twilight, but it's such a beautiful and magnificent crater. It is well worth your time. I still remember many, many years ago, the first time I ever caught sight of this thing. And I thought there was something wrong with my telescope because it was so perfect. That big canyon, the rill that goes from the central peaks out to the rim is more than 50 miles long. And it's absolutely straight in my 90 millimeter refractor. And it looked like somebody had scratched my lens. It did. It was beautiful. Petavius is named after a Jesuit theologian. And it's an interesting fact that of the 100 largest craters on the near side of the moon, 34 of them are named after Jesuits and 6 more on the backside of the moon. So there are more Jesuits on the moon than anybody else. And that's just a fun fact to know. This is a huge crater. Excuse my non-metric measurements, but that's just me. It's about 110 miles across. The walls around it are 2 miles high, which make it one of the deepest craters on the moon. The central peaks are over a mile high, and which again is very, very large for a crater. It has a complex series of rills called the Rimae Petavius all through it. The picture on the left is what it looks like from the Earth, from your telescope, because it's near the edge of the moon. The other one was taken by an orbiting satellite going around the moon, so you're looking straight down on it. And of real interest is what they call the railroad track. You notice where the large canyon hits the wall, and then there's a double line feature that goes around called the railroad. I'm not sure what that is. I don't know whether that's a fault or what, but it continues all the way off the south down. It continues beyond the crater down. And if anyone knows what that is and can tell me, I would love to know. But it's a beautiful, beautiful crater. Take your time while you're setting up before the sky gets dark, before the moon sets, because you only see it the third day after a new moon. By the fourth day, all the shadows are gone. And it's nothing to look at anymore. There you go. Any questions?
Terrific. That's terrific.
That's it.
Thanks, Bob.
Next month will be another feature.
Thanks, Bob. And that's so cool. A 2 mile high wall. That's just insane. And it looks like a giant moon buggy rode along the rim and kept going.
Oh, I forgot to mention the dark spots on the right side of the floor of the crater, showing that there's volcanic activity after the crater was formed. Lava welling up from beneath those smooth dark spots, which are visible even in my 4-inch refractor. I could see those.
Wow.
Easily.
Wow. Okay, that's awesome. Thank you. So Jim, you want to?
Sure. So kind of let's do a planet roundup of what we can see over between now and our next meeting. You may have caught Venus. It's beginning to get easier to see. It's pulling away from the sun. It'll be about 12 arc seconds in size and 85% illuminated. So it's kind of like a gibbous phase. Not a lot of detail, but it's kind of fun to watch Venus go through its phases. Mars is gradually, we're pulling away from Mars. It's down to about 8 arc seconds, which is really pretty small. The people say if it's below 10 inches, 10 arc seconds, it's not worth it. But it's really still pretty well placed. And if you're an imager, you can still grab some interesting shots of it. I had one here earlier this month where you could actually see a cloud formed over one of the what's called the RG basin. Jupiter is starting off lower and lower each evening. So if you're going to take a look at Jupiter, grab it during early twilight. That's where it's going to be at its highest. And also you tend to sometimes get really good seeing right at twilight. The atmosphere kind of settles down for a little bit before we start radiating the heat back out. The green comet, which somebody's already mentioned, ZTF is on its way back out. Although you can still find it in a medium-sized telescope, the main show is pretty much over. It's just going to be a little kind of nebulous-looking circle if you're able to find it. Mercury and Saturn. Saturn actually reaches conjunction with the Sun today, and Mercury, this is not a very good appearance of Mercury, so those are kind of off the table. And we don't have any really significant meteor showers this month either. Next slide, Victor. The highlights for the month are probably going to be Ceres, which is going to be at one of its better oppositions. It's going to almost reach, well, it will actually dip below 7th magnitude. It's not going to be this bright and this good again for many years, almost 10 years. So if you ever want to kind of see Ceres, this is a great time to do it. The other thing that's kind of interesting is that it'll be kind of traipsing through the Virgo cluster. And for those of you with telescopes, it's got a disk size of not quite an arc second. So what would be kind of a neat test, just like trying to see if you can get Jupiter's moons to show as more than just a point of light. Can you actually discern a disk of Ceres? So that might be a fun exercise. And then finally, we've got a very close conjunction of Venus and Jupiter coming up on February 28th, March 1st. There are details in Sky and Telescope. They're going to be about a half a degree apart. This might be a great chance in the afternoon to go out and to try to do a daytime observation of the duo. If you've never tried it, maybe give it a shot. Venus, you can definitely catch, especially if you have binoculars, but even with your eye. And then since Jupiter's going to be so nearby, maybe see if you can detect Jupiter with your naked eye as well. Our dear friend Herman Hine, that was one of his specialties, was showing people the planets or stars even during the daytime. So maybe get out there and in Herman's memory, give this one a shot. And that's it. We'll have more stuff next month.
Awesome. Thank you. That's really cool. I think I might try to do that, maybe with binoculars. Okay. Jared, I'm going to let you share your screen.
Need 1 second. I should have it in just a second. This is why I should have sent my slides, Victor. There we go.
It's all good. It's a new format. We're all learning what we're doing here.
Oh, we're out of time, Jared, so it's been.
Yeah, you know what? I'm in a situation where I'm forced to unlock a section of my computer from a preference perspective that's going to prevent me from sharing my slides, Victor. So if you want to continue in the interest of our guests, we can always circle back around afterwards and I'll share my slide.
Okay, that sounds real good.
Thanks.
Okay, one more. We've covered the sun, the moon, the planets, the deep sky. What else is there? Well, Wayne, you're up.
Hi, so I'm going to be doing a feature called What's Up in Space. So if you go to the next slide. So it's going to be a regular feature. It might not be monthly. I'm going to reserve the right to bow out occasionally, maybe. But mostly I'm going to give information about and or from space-based astronomy missions, and specifically missions like JWST, the Hubble, Chandra, XMM, Newton, Gaia, and that sort of thing. I'll generally not include any solar, lunar, or planetary missions because, well, as you just saw, we have people doing solar, lunar, and planetary. So when I'm doing this, my focus will, again, generally be on the astronomy. But I will try to work in some mission aspects when they're relevant and I think interesting. So finally, on this slide, there's a generally good thing to remember, which is Newton's second law of motion. Ignore that dot before the F in F equals ma. That's just the bulleting. So F equals ma. Now, this is actually irrelevant, what I want to talk about, but longtime HAL members will know I can't do a presentation without an equation, so here it is. Next slide.
I should put it, I should have accidentally put a triangle in front of that, and then it would be the divergence of F equals ma. Sorry.
Yeah, that would be wrong.
That would be wrong.
So this month, I'm going to talk about some JWST observations of a galaxy by the name of LIDA 2046648. Isn't that a catchy name? So as you can see over on the left, this is not a this is a newly released image, but it's actually not a newly obtained image. It was actually obtained back during the commissioning phase, back sometime before July of 2022. Okay, the image that I'm showing here is actually a crop of the full released image. This is about 10% of the image that they released. So it's a pretty good close-up. This is about 16 hours of exposure time. At least that's what the proposal listed. They didn't tell me what was actually included in the image, so I'm assuming it's all of it. This galaxy is in Hercules near the center of the keystone, if you're familiar with the constellation. And so talking more about LIDA 2046648, the type of the galaxy is an SBC. So this is how if you aren't familiar with galaxy typing, this is how we type galaxies. The capital S at the beginning tells us it's a spiral galaxy. The capital B tells us it's a barred spiral. And if you look closely, you can see a bar going across the center of the galaxy pretty much horizontally in this image. And the lowercase c tells us that this galaxy has a small bulge component and widely spaced spiral arms, not tightly wound, it's widely spaced. So this is generally how we type galaxies in astronomy. If it's not a spiral galaxy, it's an elliptical galaxy, and instead of that leading S, it would be an E. And the final letter in this case, the C, you can also have A, B, and D. A's will have large bulge components and tightly wound spiral arms. B will have a smaller bulge component and less tightly wound, etc. So it's kind of a gradation of features. I will say that this type is actually my estimate of it, because when I looked it up in the catalog, it just had an S question mark. These were that typing was based on the Sloan Digital Sky Survey images, which are ground-based, and it was determined actually by the Galaxy Zoo Citizen Science Project. Okay, so since JWST provides sufficient resolution that we could see better, I making a guess that it's an SBC. One caveat on that is this, of course, is JWST, so it's an infrared image, and typically we don't type galaxies with infrared, just historically. So if you took a higher resolution in the visible, that might not end up being an SBC. Observationally, its brightness, its B magnitude is about 17. So it's pretty faint. You're not going to go out with your small telescope in our skies and see it. It's pretty faint. Its size is only 36 arc seconds by 18 arc seconds. And it's moving away from us at about 26,000 kilometers per second. So it has a redshift then of 0.087. So it's actually a relatively nearby galaxy, even as faint as it is. Remember, we're looking at more distant galaxies at redshifts of about 12, 13, something like this. And this is less than a 10th. So its distance works out to be about 1.2 billion light years, or 370 megaparsecs. Just for comparison, this is about 23 times farther away than the Virgo galaxy cluster. So it's pretty far away, but not very far away. And I should say that most technical info came from the Hyperlita website, which URL is there. And you can see the press release at that URL down across the bottom. This was taken with the NIRCam instrument, and it was so I'm into now away from the astronomy, I'm into the mission stuff. It was obtained actually to demonstrate the ability to do parallel observations between NIRCam and the near-infrared imager and slitless spectrograph, the NIRIS instrument. Because this was a commissioning proposal and it was just demonstrating a capability, there was actually no specific science proposed for this image, because partly because they didn't know what they were going to get in it, because it was the NIRCam was not determining the pointing of the telescope. So they didn't really know what was going to be in it until it got scheduled and they knew what the role of the telescope was and all this kind of stuff. So anyway, with that,
Wow.
I'm going to be done and I will continue doing these kinds of things.
That's
every month,
awesome.
hopefully.
That is so amazing. I mean, that's a billion, like that much detail in something that's only 36 by 18 arc seconds is insane. Can you repeat what you
Yes, it is.
said about and I see Arjun has a question, but can you repeat what you said about it might being different in visual versus an infrared?
Sure. Because of the difference in the wavelength, you're seeing different structures. So the appearance will be different between, say, a blue plate, which is where we typically classify galaxies, and the infrared image that we see here.
Okay.
Okay, and
it's
so
you're
since
just saying-
it'll look different in the blue, you might actually classify it differently.
I see. I first, when you first said it, I thought perhaps the infrared was looking farther back in time and it had evolved. Like you're seeing it later with visual and it had changed from a spark
no.
to, okay.
No,
All right.
it's not changed. So it's just that it'll look different.
I see.
Okay,
Cool.
Arjun, you had a question?
Oh yeah. Actually thinking about it, my question was kind of wrong because I was assuming that it was visual, but it is infrared. But like sort of like there's V for visual magnitude. It's like B the standard for the infrared magnitude?
No, B is actually blue. In the blue part of the spectrum, it looks about magnitude 17. In the
Okay.
infrared, what's called K band, which God, I think is 2.2 microns. It's actually a magnitude 13. It seems brighter in the infrared.
Okay,
Daniel.
so
Go ahead. Sorry, Arjun.
yeah. So the B is like for like visual or for infrared?
It's B is blue. It actually
Okay.
means blue. If you look at it if you take an image through a blue filter,
It appears
look at it through blue.
Okay.
That's cool.
So that's part of the visual spectrum. Yeah, but it's blue.
All right. One last quick question, then we got to move on to our main speaker. Go ahead, Daniel.
You're muted, Daniel.
Forgot. Let's see if I can refresh my memory with redshift. What are the numbers after redshift? Mean like redshift 13?
Redshift is an observational number that's just the recession velocity divided by the speed of light.
So it means the speed at which it's traveling. Is that what the number means?
Yes.
The velocity and the speed of light, the speed it's traveling. Got it. Like,
Yeah, the 0.087 is literally just this 26,000 kilometers per second divided by the speed of light.
it's based on.
It also tells us the wavelength shift of the, say, the emission lines that are coming from the emission nebulae.
And that's supposed to also better give you the distance.
Yes, it's related to distance through the Hubble constant.
Thanks. And I tried looking at my comet tube with my binoculars, and I didn't, when it was closest, and I didn't really succeed in looking at it really well. I guess it's hard to see through an eyepiece through binoculars. It's not that powerful enough.
You're talking about the comet?
Yes.
Yeah,
Yeah.
the nights when the comet was out, the moon was kind of too bright. I also had trouble finding in the comet.
I did.
They say, so Daniel, we're gonna have to move on, okay? And so Victor will come back to you after the guest presenter, all right?
Yeah, we'll have time to talk after. So without further ado, we have an excellent speaker. Dr. Stickle is a planetary geologist with a background in aerospace and mechanical engineering and impact processes on planetary surfaces. She specializes in hypervelocity impact processes and dynamic failure of materials. How cool is all that? Dr. Stickle is currently a senior research scientist at the Johns Hopkins University APL. She's deputy PI, principal investigator for the mini RF radar, and a co-investigator for the LRO LAMP instrument aboard the Lunar Reconnaissance Orbiter, the photo that Bob showed earlier. She is the impact modeling working group lead for the double asteroid redirection test, DART, and that's what she's going to be talking about today, and the co-investigator on the Dragonfly mission. When she has time away from that, her research includes analyzing young impact craters on the moon to better understand ejecta emplacement processes, impact modeling on asteroids and rocky icy bodies, planetary defense testing, and working to understand and evaluate available technology for future lunar surface missions. Asteroid 36986 Stickle is named in her honor. Welcome.
Thank you. I feel like I should send people like a just short bio. It's always intense when that gets read. But
it's fun reading all that.
Thanks for having me. I'm really excited to be here and talk DART with all of you today. DART is one of my favorite things to talk about. And I've been on the DART mission for 10 years before it was a mission. And it's been sort of the highlight of my career. I joined right after I graduated. So it's really a fun thing for me to talk about. And if I do this, it's going to take over my screen. Are you seeing the right thing or the wrong thing?
We are
Seeing your presenters.
All right. Is that better?
That's better.
Cool. And now I can't see any of you. So, but if you have a question when I'm talking, you can interrupt me or save it for the end. I won't be able to monitor the chat, but you can put it there. We can come back to it if you want. And I will do my best to get through this so we can talk a little bit at the end. But again, yes, thanks very much for having me. As Victor said, I am the impact modeling working group lead for DART, and I work at the Johns Hopkins Applied Physics Laboratory in Laurel. I'm really excited to talk to you about DART. So this is my favorite transition slide. DART is one of my favorite missions because I find it absolutely ridiculous that we built a spacecraft and then crashed it into an asteroid on purpose. And everybody was really excited when we crashed it into an asteroid. It's very different from every other mission that I work on when you're trying really hard not to crash your spacecraft. And so it was a very fun experience, and it was a very fun thing to be able to work on. And it was just, it's been an absolute awesome past few months since we crashed into Dimorphos. So sort of set the stage a little bit. This is clearly an audience that knows this, but you know, the Earth is really frequently hit by stuff. We are hit by debris, by hundreds of tons of material every single day. Most of this is real small, little dust bits, burns up in the atmosphere. Occasionally it's a little bit larger, like the little object that came in over Europe earlier this week. And you get these beautiful fireballs, but still the things are small and we don't worry too much about them. However, there are also a lot of not so small things that can come in at us. And so this is a map put out by the folks out at JPL, looking at fireballs that have been reported by various sensor networks across the globe. And you can see that the whole entire globe is hit. It's a very random process, and it's hit quite frequently, actually. So this, this is sort of a smattering of sort of the larger things, the color and the size with the impact energy. And, they hit day and night, they hit all the time. This big red circle here marks where the Chelyabinsk meteor came in, which was just almost exactly 10 years ago. And this was actually a pretty small thing. It was only 20 meters in diameter, but it was made of metal. And so it created, this big, beautiful fireball as it came in, but it also, caused billions of dollars in damage. It blew out windows, it injured people. The airburst actually was a very serious event. And, this picture down here on the right shows some aftermath of the Tunguska airburst, which was also in Russia about 100 years ago. And it just blew down something like 80 million trees over about 2,000 square kilometers, was also an airburst. And so these are small objects. They're on the orders of tens of meters big, but they can cause a lot of damage if the Earth were to be, in their way and they were to come and airburst over a populated or unpopulated region. So these are things that, we know they're out there, they're hard to track. And so we know that they can be quite serious. To give you a sense of scale, this is a little cartoon of sort of how big that Chelyabinsk meteor was about 20 to 25 meters, which is about the size of an Olympic swimming pool. So if you can, give you just sort of a sense. So it's big, but it's not that big, right? And it can still be quite concerning. So you can imagine things that are bigger than that being moderately concerning, very concerning. And so, when we start to think about what might be of concern, some of these objects out there, you can look kind of in the whole solar system, things like, long period comets might come in, or, main belt asteroids might get knocked off course, things that are kind of these very, very low probability events. But there's also a lot of stuff just sort of in the vicinity of the terrestrial planets, right? So a near-Earth object is classified as anything, an asteroid or a comet, that comes within 1.3 AU. So this sort of gray area, which is about 120 million miles. Animation's not working. Come on. There it goes, sorry. And then there's sort of a subclass of these near-Earth objects called potentially hazardous objects. Sometimes you'll hear them called potentially hazardous asteroids if we know that they're an asteroid. And this is any of these near-Earth objects that come within about 5 million miles of Earth, and that they are big enough that they could do some serious damage if they were to impact Earth. And so this size cutoff is about 500 feet or 140 meters. You'll see that kind of later on. The 140 meters is kind of an important number. And these are the ones that we categorize as potentially hazardous, right? We don't know of any that are going to actually cross Earth's orbit at the time that Earth will be there, but they do cross Earth's orbit, so they are potentially of concern. For reference, Bennu, which was the target of the OSIRIS-REx mission, is a potentially hazardous asteroid. You can see its orbit here crosses Earth's orbit a couple of times. Luckily, we know Bennu's orbit really well, and we know that it's not actually hazardous, but it kind of falls in there. I like to show this image. So this is sort of a schematic of kind of why we think about this, why we worry about this. This is a graphic that shows the orbits of just 2,000 potentially hazardous objects, and there are many more than this. But the whole screen would be covered. But you can see, they're all over the place, right? There's lots of these. Space is big, so that's good. But there are lots of these, and they cross Earth's orbit pretty frequently, and so we do like to keep track of them when we can. And there are a lot of surveys, both Earth-based and space-based telescopes looking, just searching the skies for asteroids to categorize, to catalog them all. And so this is actually, I downloaded this afternoon. The cumulative number of near-Earth asteroids that have been discovered to date. And so we're up, in the 30,000 something. The ones that are kind of important to look at. So these are mostly really small guys. But this yellow wedge here are objects that are 140 meters and bigger. So this is where we get into that sort of regional damage range. And this is actually the size range that Congress mandated us to find 90% of by like the late 90s or something. We're not there yet, but we're still looking. We estimate that there's about 25,000 asteroids in this sort of size range. And you can see we found about 10 or 11,000 of them so far. So we're getting there. When the Near Surveyor mission, which is just, getting started to be designed and built, gets launched, that is going to drastically improve our numbers. Right now, like I said, we're limited to ground-based telescopes, which, as you all know, have weather and timing constraints. And then also we do have a couple of space-based telescopes that we use, but we're not necessarily designed for this purpose. And so we're working on this, and it's people spend their lives looking for asteroids. It's important because, as I said, we get hit by stuff a lot. Usually it's not big. Usually we don't worry about it. This is the small stuff. The atmosphere is a great shield. These things burn up. So you'll see bolides, you'll see super bolides, and that's what we call this fireball as it comes in. The really, really big stuff, the stuff that would kill everybody on the Earth. Luckily, we have found them all, and none of them are a hazard to Earth. So that's good. This range here, this 140 meters up to about a kilometer, these are the ones that could cause, regional devastation or, hemispherical devastation. And those are the ones that we are really working to find with these surveys. There's another sort of set in here, this 25 meter to 50 meter, which, are sizes of things like Chelyabinsk, which would probably airburst. We would probably take the hit based on national and international policies and evacuate folks and do stuff like that. But this is the range where we're looking, and this is the range where if we found something, we could really do something about it and try to deflect it if we found it in enough time. And so that is where the field of planetary defense comes in. NASA has a planetary defense office headed up by Lindley Johnson, who's the planetary defense officer. It's just the coolest job title. And the planetary defense coordination office is basically tasked with all of the different activities that are important for planetary defense. So we, searching and detecting and finding all of these asteroids, and then characterizing these asteroids. So, can we learn about their size? Can we learn whether they're made of metal or rock? Can we learn something about how they spin? So that's all done by observers around the globe. The Planetary Defense Coordination Office works to coordinate with international groups. So the United Nations has a couple of committees, other countries' space agencies. So planning and coordinating, what the response might be, coming up with policies and plans for national responses. Assessing actual asteroid hazards. So if we find a new asteroid, a new near-Earth asteroid, and predicting its orbit and assessing whether or not it is an actual hazard to Earth or not. The Center for Near-Earth Object Studies at JPL, CNEOS, has a website that has just lists and lists and lists of all these asteroids that are found and their hazard rating and things like that. It's open. It's automatically updated as soon as new asteroids are found. So if you ever want to go and look, you just go to the CNEOS website and check things out. and reassure yourself that there's nothing coming towards the Earth. And then they're also tasked with mitigation. And so that right now, luckily, because we don't know of anything that's actually hazardous, is largely in the forms of tests. So we do exercises with agencies like FEMA. We do tabletop exercises to practice, what would happen if we do like role playing. And also this is where DART falls in. So DART, the Double Asteroid Redirection Test, is the first planetary defense test mission to test our ability to impact an asteroid and deflect it if we ever had to. And DART is actually part of a much larger strategy. As I said, that there are national policies for this. There is a report that you can get online, put out by the National Science and Technology Council and the Office of Science and Technology Policy, called the National Near-Earth Object Preparedness Strategy and Action Plan. And it lays out the national policy. So when we would act, what we would do, who would be in charge. And it's interesting. You can go read it. I think it's interesting. And, there's a lot of different things that the country and the different, agencies are doing to try to better prepare us in case of a potential asteroid strike. And I don't know, my animation's not working. And DART kind of falls right in that. DART is, very clearly tied to a goal of understanding how to do NEO deflection, but also to increase international cooperation. We have a very large international team looking at modeling these things, and also like working with the observing people, the observers around the world, to look at how you would, detect and track and watch these sorts of things. So we fit kind of right in the middle here, which is kind of nice. And so just to give a little bit more of a sense of scale on this. So like I said, there's lots of these asteroids that we're trying to find. Most of them little, we don't really care so much. These sort of few meter ones, things like that just came over the English Channel. I think they found the meteorites in France the last couple of days. Are a few meters big. We get maybe one a year. Get a flash. It's cool. There's meteorites. Hundreds of millions of these. We have not discovered very many. As you can imagine, finding a 4 meter size thing is very difficult to find in space. So we just don't know very many of those are. Things that are tens of meters, we get hit by once every 100 years. So things on the size of Chelyabints. So statistically, we have another 90 years until another one of these comes. There's about 5 million of these. And again, we've only found a small percentage of them. These really big things that, killed the dinosaurs. Luckily, we only get hit by one of these every few hundred millions of years. Like I said, there's only a few of these that we know of in the solar system, and we know where they all are. The things that are about 1 kilometer big, these would cause a crater that's probably about 10 kilometers big. They could create, tsunamis or climate disasters that could cause global devastation, large wildfires, things like this. And we think there's probably about 900 of them, and we have found most of them. And then the other ones that we're really concerned about here, again, are these things that are about 140, 150 meters. They don't come out very often, about one every 25,000 years. And we think there's about 20,000 of them. And we've found about 40%. So, we're getting there.
Hello, Angela. Hey, Arjun has a question for you. Arjun, you want to unmute and ask your question?
Yeah, sure. So my question was, so in these graphs, you have the located and not located. How are you able to know how much you've not located when you haven't detected them yet?
It's a really good question. And honestly, it's a guess, but it's a pretty educated guess. So we look at models, and we look at sort of statistics for how much material should be, around, and And then we say, some percentage of it is this size, some percentage of it is this size. And so that's why we think there's probably about 500 million of these little ones, and that comes from models and statistics. And then we have discovered a few because they come and hit us. And that's how we do that percentage. Does that make sense?
Yep. Okay. Thank you.
All right. All right. And so again, why do we really care about this? So aside from the fact that we know it killed the dinosaurs, if we take a step back, we do know that there are impact craters on Earth. We saw that beautiful picture of the moon earlier. The moon is just like littered with impact craters. And, the moon and the Earth are in the same part of space. Statistically, we would have been hit by the same stuff that hit the moon early in the solar system. And, plate tectonics, things like that has erased a lot of it. But we know that there are still relatively fresh, relatively recent impact craters on Earth. So Meteor Crater, or Barringer Crater out in Arizona, is only about 50,000 years old. We think that it formed by about a 50-meter metallic asteroid. It has a crater that is about 1 kilometer big and about 180 meters deep. And you can see these circles on here are sort of the range of place where the devastation occurred from this impact, out to tens of kilometers. So there was a fireball that occurred out to about 10 kilometers from the crater, out to about 24 kilometers. You get a shock blast that can kill or wound large animals. And out to about 40 kilometers from the impact, you get hurricane force winds. And so this is like a very regional devastation that would knock down buildings. It would, kill anything in the area. And so this is something that's relatively small and happened fairly recently. So it is something that we think about. And if you overlaid that, for instance, on, everyone's favorite place to live, you can see that if something size of the meteor, the cause meteor crater, were to hit DC, we would take out pretty much the whole district, good portions of southern Maryland and northern Virginia, and out into the water. And so it could cause some pretty significant damage. We did an exercise a few years ago, one of these tabletop exercises at the Planetary Defense Conference, which is a conference that happens every few years to talk all things planetary defense. We have one coming up actually in a couple months in Vienna, where we had an impact come in Manhattan, and this was sort of a same size, 50 meters, and took out all of Manhattan. So this is sort of the size range where it starts to get a little bit concerning, and 50 meters is actually the cutoff where we would try to deflect something, probably. Well, we would certainly do something about it. And there are a variety of things you can do if you see something coming at the Earth, if you have warning time. For the small stuff, anything less than about 50 meters, like I said, we would probably just take the hit. We would know where it's coming in. We would evacuate cities. We would evacuate people. But even that, you can imagine, would be, we evacuate for hurricanes and things, but people get to go back. If you had to evacuate Manhattan and then tell people they could never come back again, it's all these things. But so there's a whole other field of folks that worry about that. When you start getting into the bigger diameters, you have a few different options for things that are, relatively small, or you have a lot of warning time. If you find it, really far in advance, you can use what's called a kinetic impactor, and DART is an example of that. And DART was chosen as the first test of this because the kinetic impactor was the most mature technology, was the easiest to implement. We knew how to do it, we thought. And so we thought that would be the first test. And you can use it on a large range of objects, and the ones that are kind of this most concern, this 140, 150 meter range. For very big things, or when we have almost no warning, you could use a nuclear device to either deflect or disrupt the asteroid. That comes with a whole other set of political issues, but it is a viable deflection strategy. And there are folks who do models of that. For obvious reasons, we can't test that, but we do model it so that in case, we were ever found ourselves in a situation where it might be necessary, we know what we'd have to do.
Hey, Angela,
Yep.
did the movie Don't Look Up actually have any merit in terms of, what they were thinking about doing and the destruction and the what they were trying to do to deflect it?
So honestly, I didn't watch it because it was a little close to home. But from what I heard, yes, actually it did. And one of they actually had a few planetary defense experts as science advisors that they listened to really a lot in the designing of it. And so I think it was fairly true to what you would do, from what I've heard, that it was pretty well done. I don't know, I probably should watch it. It was a little, the time it came out, we were all a little bit like, ooh.
Daniel has a question. Daniel, you want to unmute and ask your question? Daniel, you have to unmute.
I don't have a question, I have a comment, something I want to share with you about a movie that reminds me of this topic about asteroid deflections. There's a movie that I just came on my mind that reminded me. There's a 1998 movie, and I watched it once. It's called Armageddon, about an astronomer that observes at an observatory, and he observes an asteroid, and it's predicted to hit Earth, and they sent a shuttle crew of astronauts to detonate and explode to save mankind from Earth. Have you heard of that 1998 movie called Armageddon?
I have. It's actually one of my favorite movies. While I think what they chose to do in that movie is not quite realistic to what we would do, it's still a fantastic movie. And I like it for bringing planetary defense into the sort of public consciousness.
This is a planetary defense movie. We talk about looking at asteroids and using the government coming up with DART missions, ways to deflect it to keep it from hitting Earth and to saving mankind. That kind of reminded me, it made me think of that movie, and I just wanted to share it with y'all.
Thanks, Daniel.
Yeah, and actually that's part of the reason why DART is my favorite mission. It's very nice to say that I'm a planetary defender.
Well, maybe you can add Bruce Willis's mugshot to that chart.
Yeah, he didn't want to come play with us.
And Joseph has a question also. Joe?
Yeah. So I just put this up while we're talking. This is a nice little scrolling chart of all of the different organizations and countries that are members of the DART team. Because DART.
I'm sorry, Angela, we have one more question if that's okay.
Yep, go ahead.
Go ahead, Joseph. You're muted.
How about now?
You're good.
Okay. Yeah. Hi, Angela. I'm Joseph Novatka. I did work at NASA. I'm retired now. But I was wanting to inform you, I don't know, I think I just heard it today, or was it yesterday, that the meteor that went over England and into France, they found the meteorite.
They did, which is so exciting.
Yeah.
Yeah.
So you heard about that?
Yeah, it was kind of it blew up on the DART Slack. It's exciting.
That was a 1 meter meteor.
Yeah, and they're just so cool. Yeah, it's been really exciting. The last few of these small ones that came in that we saw ahead of time, we knew they were coming in. I think there's been 4 of them in the last few years, and for all of them, they were able to predict where the meteorite pieces would land and go find it. So it was really exciting when they kind of like, this is where it should be, and that's where they were. Yeah, so that it's exciting when you get to, it's like origin story coming in. Yeah,
that's great.
Yeah, so let's see if I can get this to scroll again. You saw the long list of things that people go by. DART, the team for DART, so the spacecraft itself was designed and built at the Hopkins Applied Physics Laboratory for NASA. But the team is actually worldwide. We have about a 300-person investigation team on DART. And the reason that we wanted to do this is because, as you might imagine, and from all the things that I've said, that, you know, planetary defense is really a global concern. And so we want global responses. We want international cooperation. We want as many of the voices in the room that know what they're talking about as possible so that we can, you know, better prepare ourselves. And this is an image that we took just about 40 days after impact. We had a team meeting at APL. We had a hybrid meeting, you can see here, of our investigation team. There's lots of very happy, very smiling faces because we were still getting fresh results. Yep, outside of building 201. You know, we have these hundreds of people from across the world. And it's been such a treat to get to work with all of these people that, you know, I wouldn't necessarily get to work so closely with ESA on most other things, but, or, you know, any of the various other agencies we work with anybody who will work with us. So it's been very fun. And now let's get into DART. So DART launched on November 24th, 2021, just before Thanksgiving. It was about 10 degrees. It launched at 1 a.m. and we were outside of building 200 at APL watching it go up on this big screen. It was very cold, but very worth it. It launched out of Vandenberg Space Force Base on a Falcon 9 and had a very short cruise, actually. The target asteroid, Didymos, or asteroid system Didymos, was making an exceptionally close pass by Earth. And so we only had a few, you know, less than a year-long cruise. We impacted the moonlet of the Dimorphos system on September 26th of last year at 7:14 p.m. I hope many of you got to watch it live with us. I think NASA did a fantastic job with the broadcast. And the goal was to hit this 150 meter-ish object and measure how much we deflected it. And the way that we did that was by measuring its period change. We had a little ride-along satellite called Licia Cube, which was built by the Italian Space Agency. And it had 2 cameras to take pictures after the impact. We had 4 I don't know, we're still up in the air on whether we're past tense or present tense for DART, because it's still going. We still have, you know, the science team is still going, but the spacecraft is no more. But we have 4 level 1 requirements, which are sort of the mission success requirements for a NASA mission. The first one was to impact Dimorphos, which we did beautifully. The second was to change the binary orbital period by greater than 73 seconds, which if you had been paying attention to DART at all, you would know that we did that, and I'll have some more results of that later. Number 3 here, actually, we just called success on a few weeks ago, and that was to measure the period change to basically within 10%, to within 7.3 seconds using ground-based observations. And we've had an absolutely phenomenal observing campaign and observing team on DART, and they have been working so hard. Didymos has basically been up in the sky since October. It's receding now, and so they finally get a break, but I'll show some of those results later. And then the last goal was to measure this thing called beta, which I will talk about in a little bit, which is, you know, tells us how big of a deflection we got, and then also to characterize the impact, what happened for the impact crater, what happened to the system dynamically afterwards. All right. So like as I said, this was sort of, you know, we picked Didymos as our target, sort of this ideal time to be doing this. So you can see this little animation. You have Earth going around here in the middle, and then this is the Didymos system coming here. And we launched, and Didymos was kind of, you know, pretty far away. But as, you know, we had this short cruise, you see that Didymos and Earth's orbit come very close to one another. And so actually we put DART in its way, and Dimorphos crashed into us. So I say that Dimorphos is the aggressor on September 26th. And this was really important, this timing, because it allowed us to watch from Earth, right? So the Didymos system, I think this is a movie also. The Didymos system has a primary asteroid, Didymos, about 760 meters in diameter. And there's a little bit over a kilometer separation to Dimorphos, which is the little moonlet here you can see orbiting. And so we launched DART in November. Right, a few days before impact, we dropped off Lichia Cube. We impacted, Lichia Cube flew by, took some pictures. And because of that impact, we slowed down Dimorphos's orbit. And we watched that change from Earth-based observations. And that was really only possible because Didymos was so close to Earth. No, it's doing it again. DART looks like this. This is the DART spacecraft, was the DART spacecraft. And DART is a technology demonstration mission. So we were demonstrating multiple things on DART, actually. So the technology to target an asteroid for planetary defense was sort of the main test of DART. And we did that using an algorithm called SmartNav, which was designed at APL to autonomously target the asteroid. And we did that using the Draco camera here. You can see this camera here. And Draco is a telescope that it's a derivative of the LORRI camera on New Horizons. And so it's designed and built for DART. But we were also testing several other technologies on DART. So we carried the NEXT-C ion engine, which is a new generation solar electric propulsion that has been designed by NASA. So we were testing that. We had these rollout solar arrays. So you can see here, these were our solar arrays. And I'll show a few pictures of the spacecraft in a second. They rolled up like paper towels for launch, and then they were deployed out in space. And when they were actually deployed, it's about 30 meters. It's the size of a school bus. While DART, the main spacecraft itself, we had various comparisons, but sort of the size of a vending machine. We had a new high gain antenna called a radial line slot array that we were testing. This is actually the same sort of antenna that will be flying on the Dragonfly mission to Titan. And also we had these new transformational solar arrays that we were testing that were kind of these little things on the ends of the ROSA to provide more efficiency from solar power. And we also carried Lichia Cube, this little CubeSat, to show, using CubeSats for deep space exploration. So we had all sorts of technology demonstrations, and it was very exciting to test new things. And I think we got some really good data from a lot of them. And of course, DART itself showed the technology of planetary defense. Lichia Cube is the light Italian CubeSat for imaging of asteroids, designed by ASI, which is the Italian Space Agency. It was a 6U CubeSat that kind of sat on the side of the DART spacecraft, based on the Argo Moon CubeSat, which went up with the set of Artemis 1 CubeSats, and had two cameras, and they are named Luke and Leia, to look at the impact. And so I'll be showing some pictures for them. They worked phenomenally. We were so lucky to have that there to give us images of the impact itself. And they flew by about 3 minutes after the impact. We didn't want them to get like sandblasted by the ejecta, and sent pictures back. They sent hundreds of pictures back over the next couple of months. So to provide you a little bit of scale before I show the pictures to you. Here is a bus, and then here is the DART spacecraft, and some other sort of notable, things that you might know the sizes of. If you've been to Paris, Arc de Triomphe, or the Statue of Liberty is, 9 times as, not 9 times, four-ish times as big as DART. Dimorphos itself is sort of the size of the pyramids of Giza. And then Didymos is, sort of the size of this giant building, One World Trade Center. So you can see kind of how this system falls into sort of more recognizable landmarks maybe. But DART is really little, and it's hitting something relatively big. So you can imagine a bus running into a pyramid, kind of the size scale that we're talking about. And this is what DART actually looked like. So this is DART being built in the clean room at APL. So you can see the main structure here. This is where the fuel tanks were inside, and as we were building it up in May of 2020. This is September of 2020. So the DART build team was working, of course, during very difficult circumstances, sort of the spring of 2020, to get the spacecraft built, and they did a wonderful job. But you can see here, the panels are getting put on. You can see all the electronics as we're closing out the panels for the spacecraft. This is the solar arrays, so you can see just how massive they are. They were built out in California, and you can see here, this is them as they're rolled out, and they're basically just like a fabric. So they roll up, and then they have these sort of these booms they're like snap bracelets. So they kind of, when they straighten, they stiffen, but then they roll up real tight. And then this is the Draco camera. You can see we're looking up the telescope here as it is on the spacecraft. So this is the lenses down into the telescope. Lichia Cubed got to APL in August of 2021. You can see here it's a 6U CubeSat. It's about the size of a shoebox. And then this is Lichia Cube mounted on the side of DART. So this is one of the exterior panels. And we had this little box that it sat in and then got released before impact. DART got driven from APL to Vandenberg Space Force Base. They put it on the back of this truck, and they had a couple of chase cars, and they did not stop. They only stopped to get gas and to change drivers. And they drove straight from APL to Vandenberg and dropped it off for integration onto the rocket. I heard some interesting, I heard that was a very grueling road trip for the folks that had to follow along.
How long a drive was that?
It took them something like 4 days, I think, and nights. They drove through the night also, maybe 5. Yeah, it's very long.
They drove directly from APL to Vandenberg in California.
They did, yes.
Wow, it's gotta have a combination of two drivers. One drives and the other at night, the other one sleeps while it's moving.
Yes, absolutely. And that's the only times they stopped, was to change drivers. And they actually had 3. They had a three driver shift. It was very well planned. But they didn't want a chance of getting stuck on the road somewhere. So it got driven out to Vandenberg in September. Got integrated onto the rocket. So here is DART inside the fairing. We had our own rocket, and it was this teeny tiny little spacecraft in this big giant fairing. And this is a member of the integration team from APL looking at DART before it gets closed up. And then, of course, this is DART inside the fairing in November of 2021, ready to be launched. It launched on a Falcon 9, and it had an absolutely beautiful launch, as I said, right before Thanksgiving in 2021. And it was 1:21 in the morning Eastern time. And you can see here as it goes up, the weather was beautiful. There was not, cloud, it was not cloudy. And so it just was this picture perfect launch. All right, so then DART had about a 9-month cruise. And I'm gonna skip forward because that was not super exciting, to September 26th of last year. And we can relive it because I really enjoy reliving it. Oh shoot, actually, you probably can't hear it. Let me share the sound. I don't know if I did that.
I think
we
we
hear
heard
people
something.
talking. Yeah, when you hit the play button, we could hear it.
Unbelievable clarity of images there.
So this is the broadcast.
Oh, wow.
Awaiting visual confirmation.
All right.
Everybody went crazy at this picture. And then they went very crazy at this picture. This was the picture we were all waiting for.
In the name of Planetary Defense.
I still get goosebumps every time I watch this.
Fantastic.
So that's the folks in the control room. Most of us were, outside at APL watching this incredible moment. I don't know why that date won't go away.
I'm starting to see it.
Did it again. And so we impacted. Like I said, I still get goosebumps watching that movie. So it was. I hope some of you got to watch it. It was really remarkable. And then the last several months have been just so much fun learning about what happened afterwards. So we're going to step through this kind of a little bit more, and then we'll get to the cool observation photos. So this was a little movie showing the last month of essentially of the optical navigation that DART was doing. You can see this. Hopefully, you can see that little blue box. That is DART seeing the Didymos. Didymos system. Sorry, it's kind of late. And just tracking it through the sky. Like that's where we're headed. We know where we're going there. And so this is the asteroid system, and this is DART tracking it as we're traveling from Earth to Didymos. We were moving so fast that you cannot have a human in the loop for these sorts of things. DART hit at 6 kilometers per second. And so this has to be done all autonomously. And essentially from the last 4 hours, it was all autonomous navigation. And what's terrifying about that is at 4 hours before impact, this is what we saw. This little thing right here, that is the Didymos system. We didn't actually see Dimorphos until about 50 minutes before impact. It actually peaked out at about an hour. That was right when I got to be on the broadcast. It was very exciting. We'd just seen Dimorphos. But, that's an hour before we're going to impact. So, this is here. The last 2.5 minutes, this is what we see in the last 2.5 minutes. This is the Didymos asteroid. This is Dimorphos. We completely stop all thrusting, all navigating, all everything, and we're just coasting from that point forward into Dimorphos. And then 2 seconds before impact, this is the last complete image that we got, and you can see this beautiful boulder strewn surface. This is a quote that one of our GNC folks said, and I just really love it, because if you think about this in terms of like the United States, essentially we were coming in, if we're over Indianapolis, we'll completely stop maneuvering. DART hitting Dimorphos is essentially coasting all the way to Baltimore and landing inside Camden Yards. So it was this remarkable final 2 minutes, and this just remarkable accuracy that they needed to hit this asteroid, and they did it successfully, which is just, I think it's fantastic. See a little bit in the chat. Let's see. So Arjun, yes, we did a lot of research to try to understand what the asteroid might look like prior to DART getting there. We didn't have any good images. We had a radar observation, but no actual images, and so we had to do a lot of guessing based on what we knew about other asteroids. We thought that it was probably going to be bouldery, but we didn't know for sure. We knew that it was going to be rocky. We knew that the Didymos was an S-type asteroid, so a specific kind of asteroid. And so we did our best guess, and we did a lot of different models. Some of them were correct and some of them were not ahead of time. And yes, the texture will affect what we see in the ejecta. Not as much the composition, but definitely the boulders and the shape are all really, really important for what happens with the impact. And I will show that in a few slides, actually. So to step through this again, just because I think it's marvelous. 4 hours before impact, SmartNav targeting begins. This is the image that we got, about 56,000 miles from system. 73 minutes before impact, so just over an hour, we first detected Dimorphos, and that's this little smudgy bit here, just peeking out. So it was orbiting and came out from behind of Didymos. And that was really very exciting. There was a lot of chatter going on among the team, being like, do we see it? Is it real? And then about an hour is when we confirmed that yes, we do actually see it. And that was about here. You can see this is Dimorphos, and this 50 minutes is when SmartNav, the computer system, targeted Dimorphos instead of Didymos. So up into 50 minutes for impact, we were targeting Didymos because it was the only thing we could see, and then we shifted the target to Dimorphos. And this is a little picture of that. So this is actually what the guidance engineers saw. So you can see purple is showing you Didymos and green is Dimorphos. And you can see on the left is the actual visible image that the camera was taking, and then they saturated it for the algorithm. And so this is when we get to 50 minutes before impact and we target onto Dimorphos. You can see the box would disappear, and you could see that it shifted over, and as we're coming in, you can see we're targeting the very center of that blob, which is hopefully the center of the asteroid. And then this is the last 5 seconds. And then this is about 1 second before impact, and so we only got the partial image back. And this is everybody on the team's favorite image, which is kind of ridiculous because you can't see very much. But this was yeah, I don't think I've ever screamed that loud in my life as when this image came back. Oops. And then, so this is what we're seeing in image form, in case they don't move, in case the movies don't work. This is our last full image of Dimorphos. So this is, we call it the fish, the little fish that's swimming. So if you ever see a picture of Dimorphos, the way that you know that it's facing correctly, because of the optics of the telescope, you have to flip the images. You see the little fish tail here, his little mouth and his little eye, and now you're never going to be able to unsee that. But he's swimming up to the left. And so this is Dimorphos, our beautiful impact site. The spacecraft hit actually almost dead center in the middle of these 3 boulders. These 3 boulders just recently got names. So the IAU approved the naming of these 3 boulders. Features on Dimorphos are named after percussion instruments. That is the theme that we chose from around the world. And these 3 boulders are, so I can do it, Otabaki Saxum, Boron Saxum, which is the Irish Scottish drum, and Cockavilla Saxum. I don't remember the other ones are, but there was a nice press release about them. The nose also has a name, and then so those just came out. If you want to look those up, it was very exciting. We will be naming other features, and they're all named after percussion instruments, as I said. This boulder here, Otabake, is about 6 meters, so from end to end. So basically the size, 3 times DART spacecraft size. And this one I think is closer to 2 or 3. So this is about the size of the DART spacecraft. These are the final images. You can see there's a flip correctly, you see the fish is swimming, but this is what we're seeing coming in. And these are some of the main images that folks on my team are using to try to understand what happened after the impact. You can see the boulders and try to understand the shape and what's happening. So after, we got this image and everyone's very, very excited. The mission, of course, wasn't done. Licha Cube still got to fly by. And so this shows a little time lapse, a 6-second time lapse of the before and after impact. So Leech Cube was still very far away, still about 1 kilometer away, but you can see this is Didymos, and then this is Dimorphos, and then this is Dimorphos after DART hits. And so you can see immediately the brightening with the ejecta cloud. So I see somebody asked where the impact site was. So the impact site was basically smack in the middle of these boulders, and you can find them on the little fish, actually. They're kind of right in the middle. So we were targeting the center of brightness because you want to hit as close to the center of the asteroid as possible. And so they hit actually pretty close to the center, but you can see these kind of 3 big boulders in the middle of Dimorphos, and that was where we hit. About 3 minutes after impact, Leech Cube flew by on sort of a closer approach, and you can see here, this again is Didymos, and then this is the beautiful ejecta coming out of Dimorphos. You see this wonderful, beautiful streamers. It's very complex. You have streamers, you've got sort of these weird shapes. It's coming off in sort of asymmetric directions. And this was the closest approach coming at Dimorphos. And then this is seeing the backside. So they flew by and kind of turned around. And then you can see here is Dimorphos, and here is that beautiful ejecta cloud coming out from the DART impact. And this is the stuff, this ejecta is actually what causes the deflection that we're most interested in. And you can see this a little bit later. Again, you can see the curtain kind of forming here. This is a little movie that they put together of this, that the OSCE team put together. And so you can see us flying in. It bounces around a little because, pointing. And we fly in close approach and turn around and come back and see. And so hopefully, I know it's kind of jerky and fast, but you can see kind of the structure of that curtain as we go through. This image was created by one of our Draco image scientists here at APL. Took the Leech Cube images, and actually each of these boxes that you see is a different stretch. So he just stretched different regions in different ways to kind of pull out this ejecta. You can see that it's just absolutely stunning, right? You have these streamers that come off. So the ejecta is not just a sort of nice cone. We do see, we think, evidence of boulders in the ejecta curtain, and I'll show that in the next slide. It's very complicated. It's not symmetric. And so this is like one of the things that we're trying to understand now. We're doing a lot of modeling to try to understand why it looks like this and what that means for the deflection. You can take the Leech Cube images, and like I said, you can saturate them and try to understand more about what is going on. And so this is an interesting one because there's a lot going on in it. So you can see these things that we circled. Hopefully you can see this. We think is like there's some boulders in there. We see evidence of maybe some boulders that were ejected from the surface here and over here. You can see, you get this kind of long, fast streamer coming out here. And so there's really a lot going on. And that we're all having a lot of fun trying to figure out exactly what's happening and why, and doing a lot of modeling. That's what I spend a lot of my time doing right now is modeling DART and modeling these things to try to understand them. As I mentioned, we have an absolutely wonderful observation team on DART, and we have folks around the world who were observing DART and continued to be observing the Didymos system since then. Here's all of the telescopes that we had on our team, the locations, and we had some people on every continent, I think. And this was very important because, as you know, it's not nighttime everywhere at once. And also, when we actually impacted, visibility for Didymos was actually much better in the southern hemisphere than it was in the northern hemisphere. And so we had a lot of folks on telescopes around the world observing with us to try to capture what's been going on. And this, maybe you've seen if it was floating around Twitter, this was the first data that came back. It showed up on the DART team Slack about 20 minutes after impact, I think, and everybody lost their minds. So this bright thing coming through, that's the Didymos system. And then you see this huge puff of material coming out. And it came, like I said, it came on the Slack and everybody freaked out. We were all running around being like, oh my gosh, have you seen this? Have you seen this? This was taken by the Atlas project using a telescope in South Africa. And it's still, the team is still trying to figure out what this is and what happens. You can see this is another view of it, but you can see you get this really beautiful hemispherical cloud of debris that came out very fast, 10 minutes post, 12 minutes post impact, and it starts spreading out very fast. And so you can see by 15 minutes post impact, it had kind of spread out in this more diffuse range. And so this is one that is still a mystery, but it's causing a lot of debate on the team, and it's one of my favorites because, like I said, it was the first one. And it was just so spectacular that it was really fun to get it on my phone. Dimorphos have enough gravity? So Dimorphos has a very weak gravity. It is, the escape speed of Dimorphos is 8 centimeters per second. But because it is in a binary system, some of the debris could come back and reaccrete. It is possible you might get something like tektites coming back to the surface. It's probably more plausible that just fragments might come back or small dust particles. Everything else gets kind of knocked out of the system. As I said, we had folks all around the world looking. So here are some images from different telescopes around the world of the Didymos system shortly after the impact, and you can start to see, we created an active asteroid. You can start to see this beautiful tail forming, and it shows up on all of the telescopes in various different wavelengths, and it's been very fun to track. We did have observations from both Hubble and JWST, which was amazing. JWST was not originally designed to track as fast as it needed to. Well, it was designed to, they didn't know if they could track as fast as they needed to track DART. And they decided they wanted to go for it, and we're so glad they did. We got these stunning images. This is a movie that was created using JWST data from before impact, and then you see all of this beautiful debris and ejecta coming out from the web data. Similarly, from Hubble, you can see this beautiful ejecta coming out. We were really lucky to get a really good amount of Hubble time. Up until just very recently, we've been getting Hubble images, and so we have a lot of Hubble data. And so, very early on, we got these beautiful pictures of the ejecta curtains. And then later on, we've been getting these just absolutely stunning images from across the team of this tail that was formed of the debris that gets sort of spread out as DART moves through space. So we created all of this debris with the impact, and then as DART moves, we leave this trail behind. And it seems like every few nights we get a new image on the DART team Slack from one of the telescopes, and it's still there. It's really fun to track. We did actually, from Hubble, about 12 days after impact, notice that we had actually 2 different tails. And that is still being discussed in the team about why that happened and what caused that. It's different than like the 2 tails on a comet, but we do have these 2 different tails that formed from the DART impact. You can see here, this is November, so 50 days after impact, and you can see this glorious tail from Dimorphos just trailing behind it. In January, this is late November, the next one's January. So late November, you can continue to see, we're still seeing it. It's getting a little fainter maybe, but it's still very much there. And even in January, this is one that came back January 25th from Lowell, and you can see the tail is much fainter now. Didymos is moving farther away, of course, right? So it's decreasing in magnitude, but also the debris cloud is sort of fading around, fading a bit now. But this is 120 days after impact, and we're still seeing this debris tail. And so the team is, like I said, the sort of apparition for Didymos is ending soon. And so the observation team is sort of winding down, but they've basically been on sky since last July, getting pre-impact observations and post-impact observations. And so there's a lot of really amazing data that they've collected and that they're getting ready to put out into the public data, the planetary data system. 15 days after impact, which is a whole month sooner than we thought we were going to be able to do it, we were able to announce that we successfully deflected Dimorphos, and we had the NASA administrator, Senator Bill Nelson, announced the period change at a press conference. And this was the first time that we have, intentionally deflected something in the name of planetary defense. And so it was a very big and exciting moment. And the team, was absolutely thrilled to be able to turn that result around so fast. The way that we learned this is essentially by looking at light curves. So that because Didymos is an eclipsing binary system, we have a light curve from prior to impact. We knew the orbital period of Dimorphos. And we would get these little, dips in the light curve whenever Dimorphos went either in front of or behind parent Didymos. And then after impact, that light curve changed. So this is the actual light curve one day after DART hit. And already we knew that we had really whacked it. The period change, it started out as an 11-hour, 55-minute orbital period. And just at one day after impact, it was at 11 hours, 23 minutes. We took a while to confirm that. But you can see how this light curve shifted with time. And this was all done using telescopes on Earth. And essentially what this, it's an eclipsing binary. What that means is, every time you either go in front or behind of Didymos, you're either in shadow or you're casting a shadow. And so the light that returns to Earth changes. And so that's relatively, not easy, I don't want to say easy, but it's straightforward for folks to be able to observe and to watch from Earth. And so this is what it looks like. These are the light curves that we have from starting in September and going through, shortly after impact. And this is where we confirmed our new orbital period. And you can see these arrows show, if we hadn't changed it, this big dip should be here, but it was actually here. So we changed the orbital period by about 30 minutes. I see your question, Kenneth, and I'll get there in just a second. We also used the Goldstone Radar Complex out in California to observe as well. And I'm used to looking at radar images, so to me, these are very beautiful. To most people, I think they just look like noise. But to guide your eye, this is Didymos here, this bright reflection. And this is Dimorphos, these bright 2 pixels. So this is actually the best picture. Something that looks like this is the best picture we had prior to impact. So we didn't know a lot about what it looked like first, right? And then after impact, this is where they are, and this is where they would have been. This is where Dimorphos would have been if we hadn't hit it. So it was really, the radar was actually really, really exciting because we were all scared after that first image that we had disrupted Dimorphos actually. But the day after impact, the radar team was like, guys, we see it, don't worry. And everybody felt a lot better. We can also look at the color or the spectra of the asteroids. And before impact, we had, it's basically a point source. But what you see is that most of the reflected light that you get is from the big Didymos asteroid. After impact, most of that light actually coming back is reflected off of this ejecta. And so we can look at what this looks like. And so this is a reflectance spectrum of Didymos. This is how we knew what kind of asteroid it was. This is a typical spectrum of an S-type asteroid. And basically it's showing that it's made up of pyroxenes and olivines and things that we assume to be in these types of asteroids. This is what it looked like pre-impact, so when it was just Didymos, and then this is what it looked like post-impact. And it changed a little, of course, but you can see that they look very similar. And so this tells us actually that Dimorphos is probably made up of the same stuff as Didymos. And this is really important because it means that Dimorphos probably formed from Didymos. In a binary system, we don't always, there's lots of theories, a few theories about how the moons actually get there. And one of them is that a lot of the material sloughs off the primary and then accretes into a little moon. And so this would suggest that that theory is correct. And I know that I'm going long and I'm really sorry. I can stop here or I can have a few more slides. It's up to you guys. I know you have other things you wanted to talk about. The other slides are just a couple of model pictures, but I think we've seen the cool stuff.
I say just go for it.
Okay.
We can go over a little bit. And,
okay.
And the other stuff, we can push off till next month if needed.
All right, I've got just a few more minutes, I think.
Well, also let's leave time for questions because I have a couple.
Absolutely, yeah. And so I guess, yeah, so I will. I'm gonna go fast and then you guys can ask questions. That's okay. So this gets a little bit to, I think, Kenneth's question. So one of the ways that we talk about deflection is this term called beta. And it basically is like how much we push the asteroid. And so you can think of it actually kind of like a rocket engine, that if you hit it with the spacecraft and it kicks up all this debris, that debris acts like an engine. And the more debris that you have, the bigger push you get. And so if you don't create any debris, you get no ejecta. You do still add the momentum of your spacecraft. And so you do move the asteroid a little bit. And then depending on what it's made of and depending on the shape and how hard you hit it, you could get some ejecta or lots of ejecta. DART has this beta factor of about 3.6 is what we are estimating, which puts it right here in the middle. And that means that we actually gave the asteroid 3.5 times more momentum than the spacecraft came in with. And so most of the push comes from this ejecta. And the way that we can estimate this is through numerical models. So this is actually what I do. We do these impacts simulations, and we can track things like pressure, temperature, crater size, how much ejecta is coming out, where it's going, as a function of what is the asteroid made of and what is its shape. And so we did a lot of simulations before impact to try to understand what we might see, because we didn't know anything about Dimorphos. We didn't know what it was made of. We didn't know its shape or anything. And what we were finding was that different things, so how porous a material was or how strong a material was, really affected how big of a push, this beta number that you get. You can vary this systematically, you can kind of scatter. We saw that this had these two parameters were really, really important for deflection. And so those are kind of ones we focused on. We also know that the structure of the body is really important. And so you can actually get similar deflections if you have different structures, but your crater is going to look really, really different and your ejecta is going to look really, really different. So we did a bunch of models of different structures and things like that to try to predict what we might see. We know that these boulders are beautiful, but also like a giant pain. They make your crater kind of weird and wonky. They make your ejecta do funny things. And they can actually affect how much push you get because they change the way the ejecta goes. But luckily it's not that big of a change. It just really changes what it looks like. And so those streamers and things that we saw in the LeachIQ images are actually because there are boulders on the surface and you get sort of smaller sandy material or finer grain material coming out between the boulders. We know that, as I said, porosity is important. And so we looked at different kinds of porosity. We looked at very solid rocks. We looked at kind of fluffy rocks. we looked at bouldery rocks and looked and see, they all gave us different deflections. And so I'm just kind of running through these because there's all these different things that we didn't know. And so we ran hundreds and hundreds of models over the past 10 years to try to better understand them. Mostly when we model things, we model them as spheres because it's, your spherical cow with no friction and everything. And it's just a lot easier. But DART, as we saw, is not a sphere. It's not solid. We know that DART itself, structure of it causes some weird things. And if you impact the actual spacecraft model into a fake asteroid, you get these really beautiful crater shapes and you get this kind of funny ejecta pattern. You get this main crater from the spacecraft and then you get these wings from the solar panels. And so, we looked at that a lot. And then, since the impact, one of the things, we've been really focusing on is to try to understand. The slide is not showing up in my thing. Is to try to understand, I don't know why that. Sorry, my little screen had a different one. To try to understand, like, what does the actual Dimorphos do? So this is our model of Dimorphos. This is looking at the impact site. You can see our 3 boulders. And so right now we're running lots and lots of models of this. This is the actual size, and this is the shape model from the team. And we have the boulder size frequency distribution as measured by the team. And I can't show you a lot of these results yet because they're not finished and also they're under embargo. But we're looking at what is the material porosity, what is the material strength, what do the boulders do, and what does it actually mean for Dimorphos now that we have these results and we can match the period change, we get a velocity change, we can match that with our simulations and try to back out the properties of Dimorphos. And so that's what my team is really focusing on right now. DART has a wonderful internet presence and social media presence. NASA has a bunch of Twitter and Facebook and Instagram stuff. You can go and take a little quiz and get an I'm a Planetary Defender sort of digital certificate and sticker. I was very excited that I passed it. I was kind of scared when I took it, I'm not gonna lie. And we also have a lot of things that you can get off of our website, actually. We have an augmented reality. You can sort of scan a QR code with your phone and drop the DART spacecraft and like walk around it. We had a school designed a toy brick model for us. And so there's instructions online. We have 3D printable models, and I think the files are on our page. You can download and 3D print a DART spacecraft or the Dynamo system. And so I would just welcome you all to go look at some of that stuff. It's really fun. There's some really great movies and images that the media teams have put together as well. And I'm just gonna leave it with this picture of a very happy mission operations team after we destroyed our spacecraft. And with that, I am sorry for going so long. Oh my gosh.
No
happy to take
apologies
questions.
necessary. That was really, really fun. Everybody's still here and engaged. So thank you. That was fantastic. And that's a great picture to end with too. It makes me happy.
Yeah, it was a really happy moment.
I just scanned your QR code, so I'm gonna do that in a minute. Thank you. We have a hand up. Jacob, you have a question? Go ahead and unmute yourself.
Hi, yeah. So I actually about a few weeks ago, a month ago, I saw the space subreddit on the space subreddit. Somebody posted something about this, so I thought it was pretty cool. I just happened to be on the HAL website like a few days ago, and I saw this, and I was like, "Oh, wow, cool! This is the first time I was on the HAL website." And so, but my question was, one of the worries was that not knowing the material of the asteroid, they weren't sure if the DART would just literally plow right through Dimorphos and just like make a hole in it. And but it looks like it didn't do that. But I was kind of curious. Like I thought that was kind of interesting that that I didn't understand that asteroids could literally be just like these clumps of rocks like that, and that was kind of one of the biggest fears. But I just kind of wanted to mention that because that just the end of your presentation brought that back up to my mind. So
Yeah, actually, that was one of the that was actually, yes, a fear, kind of just sort of existential fear of the team. One of our first missionist engineers had recurring nightmares that it was actually going to be a donut shape, and we were going to just, you know, go right through the middle because we were targeting the center. Not a real asteroid shape, but you know, these things. And actually, for Deep Impact, the mission that crashed into a comet, they were really, really scared that they might go through it because it's this icy, fluffy ball. And so we did some impact experiments into cotton candy to simulate a comet, and they're kind of hilarious because they completely explode. Luckily for DART, DART is so small compared to the asteroid that there just wasn't enough energy for us to go all the way through, but it definitely is one of those sort of existential, like, we don't know what it is. So we did lots and lots of tests.
Anybody else have some
Thanks.
questions?
Actually, I just realized I realized I just never actually answered Ken this question about the amount of ejecta. We are still working on that. We can say that there is something like more than 1 million kilograms of ejecta. I think the official term around the team is a metric crap ton. We don't know. It is something we are working on from the models and also from the observations, but it's still a work in progress. Yeah.
I have a question. Was that an FEM, a model of like a finite element model of the whole asteroid?
The ones that I was showing at the end?
Yeah.
It is a finite difference model, but yes.
Finite difference. Okay, cool.
So we have a large modeling team, and we have a bunch of different kinds of models. Most of them are either gridded or smooth particle hydrodynamics codes, and of various flavors that we model with. Yeah, and so we took the shape model that was generated from the images, and we have a set of folks who have been counting every single boulder on every single one of those images, and then we created sort of a randomized boulder field with those sizes.
And one other question: is there any chance that the Earth will pass through the debris field? Will we get an shooting star annual shooting star extravaganza named after DART?
Sadly, no. We looked at that actually. We thought maybe with all the debris, but it was facing the wrong direction. And so I don't think that there's any still left in sort of the Earth orbit. Because we asked, yeah, we did ask that. We're like, wouldn't it be cool? But no. But you can go, well, you might not be able to anymore. I was like, Didymos is fading pretty fast. I was like, you could go see the active asteroid, but it's fading pretty fast.
Well, anybody else have any questions? Well, I got to say that was really, really fun. Thank you so much. That was just, I mean, the fact that everybody's still here and it's 9 o'clock.
Yeah, thank you for having me. Like I said, I love talking about DART. So
thank you.
You guys enjoyed it as much as we did.
All right. Well, if anybody doesn't mind staying on a few more minutes, I think I'll just go ahead and show some Astro Images, and we won't have time to discuss too much, but I might as well just wrap it up like that if you guys can hold on for a couple more minutes. So again, thank you to Dr. Stickle. And next, I'll just go through some images. So Joseph, are you on? I saw him earlier. Maybe he's off now, but here's a nice M81, M82. We have a video from Jim Lane. Is Jim on?
Yep, I'm here.
All right, let's get this video up.
All right, so I'll go ahead and just talk it real quick because there's no audio. It's the comment that's out there. So I was shooting Monday night when it finally cleared up, and I shot 96 shots through an 8-inch telescope and stacked them. But as I was processing the photos, I noticed between the first and the very last, this is a 10-second video. Yeah, just gotta do it again. Thanks. Between the first and the last shot, which is about an hour and 4 minutes in time difference, I noticed the comet moving through the star field. And I thought it was the coolest thing between the first image to the last. It's like, man, in 1 hour, you could see this thing moving. And so I just turned my raw images into JPEGs and shrunk them down a bit, made a video, a time-lapse video of all 96 images. And then I had to zoom in the video because the whole star field is huge. So I had to zoom. I used the tool just to zoom, crop and zoom and blow up this. So you could see the comet just kind of doing its thing there. A couple of the stars jiggle, I got a little bit of tracking error there. But overall, I don't know how far it's moving. I didn't plot it or measure it or anything like that, but just thought it was cool. Just a different way to look at the comet. So thanks.
Very cool. I think you can maybe even see the tail there if you imagine.
Yeah, a tiny bit. Yeah, each of those shots was 30-second exposure at ISO 1000. So you can see a little bit. Yep.
Cool. All right, next we have Josh. Is Josh on? Well, this looks like a fine shot of one of our favorite objects here, M42 and Running Man.
Yeah, and I think it's very colorful too. I like the pink, purple, and blue.
Yeah, and he stretched it pretty good there.
Very beautiful.
And Josh had another picture, which is some of the, I think this is a pretty wide field of M90 near Leo. So we'll just move on since it's late. Al, are you still on? I think I see you. You're muted if you're talking. This is just a really fantastic picture of the sun. I am not a solar expert, so I'm not sure how to talk to it. But
well, it's pretty fantastic. It really is. I don't know what size telescope he used or what camera, but he captured a tremendous amount of detail and really did a fine job of processing to get that detail without creating a hard edge. And you see that prominence breaking off
down at the bottom.
Yeah, down at the bottom, it's breaking off and kind of floating away. But if you were able to zoom in more, you would actually be able to see a field line that's really holding it there to the chromosphere of the sun. And that filament that's about going from kind of north to south or south to north a little bit, that thing is incredibly long. You're looking at close to probably 350,000 miles. And that's just the light, but you can't tell how far out, coming right at us. You can't tell how far that's standing up, but if it was to hold together and rotate towards the edge, it could be a pretty significant prominence coming off the edge. And then there's plenty of the white areas are plages, which is French for beach, and you usually see them around sunspots, very, very hot areas. And it's just a spectacular, well done image, great capture, and excellent processing.
Yeah, isn't it?
Yeah.
So next we've got Steve Gauss. Looks like he got some of the eclipse progression. I'm gonna just move through. Oh, you're here, Steve.
Yes. Yeah, this was back in November. I was very fortunate in that the moon was setting right between the trees in the one clear space I had in that direction. So I was able to get it with my C14 with the hyperstar, and was able to follow it right down pretty near to the horizon.
Neat. That's really cool. I think you have another one in here.
Yeah, this is, again, this is with the Hyperstar, the Rosette Nebula. I've had it for several months. A 14-inch at f2 can do some amazing things, but in the skies that we have around here, it's really tough to find a good time to use it. And I'm still playing around with the filters to get the colors the way I like them.
Nice. And then you have this one.
Oh, yeah, okay, this is, yeah, the North American Nebula. I think that was one of the first ones I did with the Hyperstar. And these are all unguided. I don't remember now the times, but they're all 30 seconds or less.
So is
Unguided
this is
exposure.
one image? This isn't stacked?
This is this is probably, I think, a 3-frame montage. The Hyperstar covers about 2 degrees.
But you didn't stack multiple images to achieve this?
Oh, yeah. Yeah, probably usually 10 to 15 images stacked.
It's pretty
Yeah.
good.
Yeah.
You're at F what did you say?
F2.
F2, yeah, that'll do it.
Yeah.
Awesome.
Yeah.
Thank you. And then James Willingham is not here, but he got a couple of neat shots of when there was that Moon-Mars conjunction. And he also got a pretty neat shot of the comet conjunction with Mars. And then also we were hearing earlier from Jim Tomney about how Mars is kind of shrinking. And here's a pretty interesting example of just what that means. So moving on, Joel.
This is where we are fortunate enough to see sunset during the winter in Punta Cana, which is at 18 degrees latitude. So the difference of our shortest to longest days is only from 11 to 13 hours. And this was the moment of the winter solstice at Lago de Coco, named after the sister of the dog there, Tika, and the egret bird that we go down and feed the fish and watch the egret go feeding for the fish each day. So that's our friend Gordon over there. Next.
Wait, you named the lake?
Well, no, actually the designer of the course, PB Dye, named the lake after his dog.
Okay. And this is for people who don't know, you're in
Dominican Republic, on the eastern tip of Dominican Republic. Actually, we've named each one of the birds in the lake. So that's another story. And then a couple weeks ago, I was just happened to be down there myself at sunset. And as I turned around on my bike to ride home, I took this with my cell phone and did a panoramic. And on the left is the sunset on the west. And then as I rotated clockwise and came around on the right-hand side, captured if you can point to the pink area above with your cursor, that pink area is the belt of Venus, caused by the sunlight coming through the denser atmosphere at the western horizon, and then reflecting off of the atmosphere opposite the sun above the slightly darker shadow forming of Earth out in space, the difference between day and night, and the blue sky above. So that pink over there is called the belt of Venus, or known as alpenglow as well. Thank you.
Cool. I'd never heard of that before. And I put Al's back in there a second time because it was so amazing. Daniel, run real quick thing, and then I think it's time to go because we're running over a little bit.
Why is the belt of Venus called so?
I might think that as am I just guessing, the fact that even that Venus doesn't get very far from the plane of the ecliptic, so that Venus might often appear in the belt of Venus, but I could be wrong on that, and we could do some little research on that, Daniel. If I do find an answer to that, I will email you.
Thanks.
All right. Well, thank you to everybody who joined, and again, thank you to Dr. Stickle. That was a fantastic talk, and thanks for coming to the HAL meeting. I look forward to communicating through email and whatnot, and seeing you again next month. So thank you. I'm gonna end the recording now, I guess.
Well done, Victor. Wayne, can you stay on for a minute? Is Arjun still here? Arjun, are you here? Yep, I still see Arjun.